In the previous video, we took a look at a variety of topics, but that mostly dealt with undirected graphs. Okay, we looked at connectedness in a sort of general sense. Here, what we are going to do is that we're going to look at the directed graph point of view. It's essentially the same as before, but there are some specificities to the topic when you discuss, when your graph have an orientation. Okay, so I'll remind you that we already saw the definition of a path, and that goes back a few slides. As much as possible, I will try to link back and forth between the results. So that was definition 23 on the 16th slide. We're at 37 right now. A path is a list of arcs that are traversed to go from one place to another. The name is really appropriately chosen. Okay, it's a path because you follow it. Now, we are going to say that a path has length 0 if it is just one vertex. Okay, so take a sequence of length 1 that consists in that single vertex, then you have your path of length 0. If you have more than one vertex, you have a path of longer length. Okay. We're going to define an equivalence relation. Again, we've seen some before. We're going to denote it like we did last time, although it's not the same relation we saw last time. And we're going to define that relation as consisting of that statement here. X is going to be in relation with Y if there is a path mu1 from X to Y, okay, that we are going to denote mu1 of xy, if there is such a path from X to Y, and also a path from Y to X. Okay, so it's not necessarily the same, but we're going to say that the two vertices are in relation if I can go from one to the other and back from the other to that one. This is an equivalence relation, and we've seen equivalence relations before, very briefly, but I'll remind you that to have an equivalence relation, what you need is for the relation to be reflexive, symmetric, and transitive. So reflexive means that X is in relation with X, which is obvious. At least there's a path of length 0 between X and itself. The relation is symmetric if X is in relation with Y is equivalent, implies that Y is in relation with X. Well, that's obvious because of the way we've defined that relation. And finally, there's transitivity. So if X is in relation with Y and Y is in relation with Z, then X is in relation with Z. And you can very easily work out that this is the case. Okay. Now, that is very important in strongly connected graphs because it's going to allow us to define what are called equivalence classes. And this is what we're going to call the strong components. So let me start with a little sort of example. Okay, I have two vertices. I'm taking a very simple example, but I have two vertices here, and let's say 3 vertices here. Now, obviously, these 3 vertices are in relation with one another, and these 2 vertices are also, because there's a path from here to there, and a path from there to here. And likewise, there's a path from here to there, path from here to there, and vice versa. Okay? Now, when you have an equivalence relation, what's very important is that it allows you to define those equivalence classes. And the nice thing is that you just need one element in an equivalence class to sort of represent all elements, because all the elements that are in an equivalence class are equivalent. Okay. So if we have sets of this form, they are equivalence classes, and they partition the vertex set. Remember that we're denoting X the vertex set. They partition the vertex set, and they are what we call the strongly connected components of G. Okay. So there might be components that are not strongly connected. Suppose I had this little piece of graph here. This one, I can go from this vertex to this vertex, but I cannot go back. So this is not a strong component. There's not a relation of that form here between these two vertices. Okay. And now, we say that a graph is strongly connected if it only has one strongly connected component. Okay, we'll also say a strong component, not strongly connected. We often say strong component. So a graph is strongly connected if it has a single strong component. And what does that mean in terms of that relation here? Well, that means that between any two vertices in a strongly connected graph, I can find a path from one vertex to the other and a path back. So this is a very strong property for a graph to have, and it's actually quite common. I mean, it depends, but in many instances you'll find graphs that are strongly connected. So I'm going to prove a little result. I'm not going to spend a long time on the co-circuits. If you remember, co-circuits are the circuits that are not in a circuit, but let's look at this, okay? So suppose I have a connected graph. So I'm talking about connectivity in a looser sense, that, well, I mean, in the sense of non-orientation that we had before, where we're looking at cycles and circuits rather than paths, okay? We're not thinking about the orientation of the arcs. We're just thinking about the edges. Okay, so suppose I have a graph with more than one arc. Then the following are equivalent. The graph is strongly connected. Every arc lies on a circuit, or G contains no circuits, co-circuits, sorry. So let's look at this proof quickly, and I'm not going to spend a long time of it, but I am showing it to you because it involves that coloring lemma that we saw earlier. Okay, so it's an interesting thing. If you want to try to wrap your head around it, please do. It's not super important, but it gives you an idea of the type of proofs that happen in this context. So if I want to show that if I have a connected graph and that it is strongly connected, then every arc lies on the circuit. Okay, this is 1 implies 2. Then let me suppose I have an arc in G. Because G, and my assumption is 1 is true, okay? G is strongly connected. So because G is strongly connected, there's a path also from Y to X, okay? Because I can go from X to Y and it's strongly connected. So that equivalence relation has to hold. I have to be able to find a path back to X from Y. Okay. So every arc XY is a member of a circuit. And we're done for number 1. Okay, for 1 to 2. Now suppose that every arc lies on a circuit, and we want to show that there are no co-circuits. Well, suppose that, and again what we're going to do is go the other way around, okay? We did that the previous time. We're doing it again. Suppose that I have a co-circuit, that it contains an arc XY. Then, by that coloring lemma that we see, that the G, the graph, cannot contain a circuit that contains this arc. If you remember, the coloring lemma told us that we could color things in such a way that either all the arcs were colored in a certain direction, or all the arcs in a certain direction were colored black, or the co-circuits were colored black and green. Well, okay, so turn back to this and you will see it. Okay, so, but that means this contradicts our assumption that every arc lies on a circuit. So it's not possible that G having every arc on a circuit contains co-circuits. Okay. And lastly, to show that if we have no co-circuits, G is strongly connected, we proceed as follows. So suppose I have a connected graph and it has no co-circuits and it is not strongly connected. I'm going to, so when you start like this, you know that what you're going for is a contradiction. So let's get there. As G is not strongly connected, okay, we've assumed it is connected but not strongly connected. As it's not strongly connected, there's at least more than one, there's at least two strongly connected components, okay? So the graph is connected if if I have a single strong component, and it's not connected, not strongly connected if I have more than one. Now, sorry. Because G is connected, when there are two distinct strongly connected components that are joined by an arc. Okay, it is connected, so I have to be able to access, but regardless of orientation, I have to be able to access all the vertices in the graph. Okay, if I forget about following the arrows in the proper direction. Now, so there must exist two strongly connected components that are joined by an arc. But that arc AB is not in a circuit because otherwise A and B would be part of the same strongly connected component. Okay. And by that lemma, that coloring lemma, this again tells us that the arc AB is contained in a co-circuit. But we've assumed we didn't have a co-circuit. So we have a contradiction. Therefore, it is not possible to have no co-circuit and not be to have no co-circuit and not be strongly connected. Okay. As I said, don't worry about it if you don't get it, but if some of you might be interested, this is something funny to try to wrap your head around. Okay. Let me give you a few results, which I'm not going to prove. Suppose I have more than one arc, and G is just a graph. I'm not assuming connectedness here. Then the following are equivalent. G is a graph without circuits, or each arc is contained in a co-circuit. Okay, so you can go back and look at the pendant of this. Here I was assuming connectedness, and you can see that G had no co-circuits. Here, each arc is contained in a co-circuit, which obviously means that there are co-circuits. What's important here is if I have a strongly connected graph, so a single strongly connected component, then the cyclomatic number, nu of G, that we saw, which is the size of the basis of a cycle basis of the graph, well, that cyclomatic number it has a sorry, this is bad. It has a cyclomatic number of nu of G equals n circuits. Okay. I'm missing a equals n here, I believe. I will check. Okay, so now we're going to look at the pendant in directed graphs to what we did when we were looking at trees. And in here, this is going to be have a different name, but let's start with some definitions that are useful for this. So suppose I have a strongly connected graph. So I'm assuming I have something like this. Okay, so let me make this strongly connected. Okay, obviously here now you can follow all paths. Just like think of yourself walking along these paths and see if you can go everywhere. So obviously here I've made that graph strongly connected. So suppose I have a strongly connected graph without loops. So there's no arc going from a vertex to itself. And I have more than, I have 2 vertices or more. For each x, each vertex, I can find a path from that vertex and a path to that vertex. Okay. So everything in a strongly connected graph, such as this one, and I mean, when you think about it, it makes a lot of sense. Every vertex has at least 2 incident arcs, whether they are coming into or out of. Remember that when we're talking about incidents, at the beginning, we're not really caring about the orientation. So every vertex in a graph like this has to have an arrow coming in, at the very least, an arrow coming in and an arrow going out. Okay. And more specifically, what we say is that if we have a vertex that has more than 2 incident arcs, such as this one here, for example, then it is a node. And if I've only got 2 incident arcs, such as here, then I have an anti-node. Okay. I can't have another situation because each vertex has to have at least 2 incident arcs. Okay. And we call branch a path whose only nodes are its endpoints. Okay, so if I have, okay, this one is not well chosen. So a branch will have, so remember that to have a node, I need more than 2 arcs. And to have a branch, I need, well, I need something like this. So let's think about a path like this. I want, what do I want? Well, it's going to be something like, and that's part of a bigger graph, okay? But this is a path, okay? It doesn't say how long it is. And here, and I should have something like this here, for instance. Okay? So that would be a branch, because the only 2 nodes, so the vertices with more than 2 incident arcs are these ones, and they're the end of that path. Okay. Now, a path is minimally connected if it is strongly connected, and whenever you remove any arc, you lose strong connectedness. So this path, this graph here, for instance, I should erase that one while I'm explaining. This graph here is not minimally connected because, okay, if I remove this arc, say, then I am losing strong connectedness, okay, because the graph is not strongly connected when I remove this one. But if I remove that guy, let me see, there's at least one of them that I can remove. Yes, for instance, this one, if I remove this arc here, I am not changing the strong connectivity of that graph. Okay, I can still move my way around. I believe, no, actually, maybe I did make a minimally connected graph. No, okay, so this one. If I remove this, I'm still strongly connected. Okay, I can still go around between all the vertices. So it is not minimally connected. So a prototypical example of a minimally connected graph would be this thing, okay? Because here, any arc that I take out, I lose the strong connectedness. And a minimally connected graph, that has to be a one graph. So between any two vertices, there's only one arrow in each direction. Okay? And it mustn't have loops, because of course if I throw in a loop here, then obviously if I destroy this loop, I am not removing strong connectedness. And the following definition is very important. I have to be careful with this thing, it's very visible. So suppose I have a graph, and we call contraction of a set of vertices the operation by which we replace the vertices in that set by a single vertex, and we replace each arc in and out of the set by a single arc with the same index. So if it's a 2 arc, then it replace it with a 2 arc, etc. And the index you keep is the same. Okay, so if I have labeled my arcs, I will keep the same numbers. And that's what's called a contraction. So for instance, let me show you. I could, let me erase this one. I could contract this graph with respect to, let's say, these 3 vertices. Okay. So if I do so, I replace all these vertices by this vertex here. And what I do is then I keep this arrow here that was going into here, and this arrow there that was, so this would be just same arrow as before, but I've just changed my target. Okay. This is a contraction. I've contracted the graph with respect to these vertices. And this is going to be quite important. Okay, another theorem that I'm going to show. I think that's all for this lecture. So don't panic. There shouldn't be many more, I believe. So suppose I have a minimally connected graph, and I take a subset of the vertex set, and that subset generates a strongly connected subgraph of the original graph. Then the graph that I get by contracting with respect to this vertex set is a minimally connected graph. Okay, so can I show you an example perhaps before I proceed with the proof? I am not sure. I should have tried to think of an example. It'll come to me probably when I'm showing. Otherwise, perhaps it will come to you as an exercise in the next assignment. So let's show the result first. So the first thing is that we're going to show that when we contract A, we get a one graph. So we're assuming we have a minimally connected graph, and when we take the set A, we have a strongly connected subgraph. Okay, and the thing is that when we contract to A, we get a one graph. So suppose, as often, suppose this was not the case. Then I would find a vertex X that doesn't belong to my set A, and vertices A and A prime in A, such that XA and X prime, XA prime are arcs, or we can think of them the other way around, okay, but it doesn't change the reasoning. But if we remove one of those, the graph remains strongly connected. So that means that the graph is not minimally connected. And that's a contradiction. Now let's look at what contraction of A does in terms of the graph we obtain. So we contract A, and what we get is a graph that is minimally connected. Okay, so A is strongly, remember that's the assumption. When we take the subgraph, we have a strongly connected subgraph, okay? So G prime that we get is strongly connected. And if I remove an arc U, then I lose strong connectedness, okay? Because the graph in which I've removed that arc U is not strongly connected. Again, draw yourself little pictures. I'm not going to do so here because I'm thinking these things would make interesting exercises to look at. Okay, but we will see. Now, yes. So suppose we have a minimally connected graph G, and G prime is a minimally connected graph that you obtain by contracting an elementary circuit in G. Then the cyclomatic number of G is equal to the cyclomatic number of G prime plus 1. So essentially, we contract an elementary circuit, and that gives us a graph that has cyclomatic number just one less. You can think of it the other way around, okay? So the G prime is that graph that I obtain when I contract my elementary circuit. Then G prime has cyclomatic number nu of G minus 1. Okay, you can think of it that way. Another result that we're not going to use, but I'm just, again, providing some notions that I think could be fun for some of you. If I have a minimally connected graph of order greater than 2 or greater, then I have to have 2 antinodes in that graph. Okay, remember, antinodes, of course, it's disappeared now, are those vertices that have 2 incident arcs only, so they're part of a line, essentially. You can go in and go out. So if I have a minimally connected graph of order 2 or larger, then I have to find at least 2 antinodes. Okay. This one is important. This one is something we are going to use often. If you have a graph, then the graph that you obtain by contracting each of the strong components, that contains no circuits. And this is something that will be done a lot, and you will see in applications. Contracting with respect to the strong components is something that is done most of the time. It's done quite often. Because it's very useful to think, well, like all these guys, for example, you're thinking about a social network, and you're thinking, well, all these people, they're quite tightly mixing or whatever. And therefore, I can think of any of them, essentially, as representing this group, and how this group is connected to the rest of the world depends on how the different people that are there are connected. And it doesn't really matter if I look at X, Y, or Z, it's all the connections that they make to the outside that are, or that they receive from the outside that are important. Okay. And so we'll often be contracting, and therefore it's important to know that if you have a graph and it is not strongly connected, it has strong components, then you contract all around those strong components, you'll get something that has no circuits. Now, we get to, I said some time ago, we look at the equivalent of trees Well, in the case of directed graphs, they're called arborescences. Still around trees, okay? Now, we call a vertex A in a graph a root if all the vertices of G can be reached by paths starting from A. Okay, let me come to make another example. Try to make it, we add some guy here, like this, and like so, for instance. So here I have a strongly connected graph, and actually you will see this soon. Well, what are the roots in this graph? All of them. Okay, because the path is strongly, the graph is strongly connected. So if you think about it, this is a root because I have access to all the other vertices from here. But this is also a root because I have access to all the other vertices from here. But I could think also of adding one guy here. That would not be a root because that does not have access to anything else. It doesn't matter if, for instance, this is something like this. Still, those two guys cannot be roots. Okay? And so we call a graph quasi-strongly connected, if for any pair of vertices there exists a third vertex, Z, from which there is a path to both X and Y. So you take a pair of vertices, any vertex, any pair, okay, so it doesn't, whatever pair of vertices you take, you can find a path to X and to Y. Okay. And that's quasi-strongly connected. Now, clearly, so this, I have an example. So this is quasi-strongly connected, but it is not strongly connected. Okay, I've already established that these two guys here cannot have access to the other. But what that means is, for example, if I take those two, because all the others are strongly connected, we don't care. But if I take those two, well, I can take any other vertex, and there is a path from that vertex, say, to this vertex, and a path to this vertex. Okay, so it is almost, hence the quasi, it is almost strongly connected, but not quite. It's quasi-strongly connected. Now, if I'm strongly connected, I'm obviously quasi-strongly connected. Okay. I just need to take, like, for example, one of the vertices as the Z. The converse is not true. Clearly, I have an example here where I am quasi-strongly connected, but I am not strongly connected. Okay. But if I'm quasi-strongly connected, I am connected, because remember, connectedness does not require you to follow paths in the arcs in the proper direction. You can follow them wherever they are. So quasi-strongly connected gives you connected. Now, what's an arborescence? It's a tree that has a root. Whoops, I forgot to move that guy, and so now it's almost in the slides. So an arborescence is a tree in which you can find a root. Okay. And there's a lemma here that I don't believe I'm showing. I think I said there won't be any more proofs. We'll see if I'm lying, or more if I've forgotten. Now, graph G has a root if and only if it's quasi-strongly connected. Okay. is buzzing. I'm recording this 3 hours after roughly UMFA announced that they were going on strike, so there's a bunch of things going on. So I just muted it. Okay, let's look at this theorem. I'm not proving it. So this is the equivalent. If you recall, last time we proved a theorem about spanning, well, about trees and the like. So here we have the equivalent for an arborescence. So if we have a graph of order 2 or more, the following statements are equivalent, and they're all equivalent to saying that the graph is an arborescence. Okay. Let's go through them briefly. So H is quasi-strongly connected and it has no cycles. It's quasi-strongly connected and it has n-1 arcs. Okay. H is a tree that has a root. You can find, it's a tree in which you can find a root. And by the way, okay, so probably I should show this. An arborescence could definitely be something like this. Nope. The oriented version of a spanning tree, essentially. Okay. Where was I? Here. H is a tree and it has a root. There is a vertex A such that all other vertices are connected with A by one and only one path from A. H is quasi-strongly connected and loses that property if you remove any arc. Okay. If you go back to that other result we saw, this will look very familiar. Another equivalence is that H is quasi-strongly connected and there is a vertex A that has in degree 0 and all the other, okay, so this is the degree of, so the number of arcs incident in to that vertex, okay? And all the other vertices have in degree 1. Okay, so you can see how this is happening. This is exactly this that we are observing here. This is an arborescence. And if I look at any vertex, my in degree is 1. I have only one ancestor in the graph, except for that guy, which is the root. And that root has in degree 0. And the last property is the same in terms of degree, but instead of stating that the graph is quasi-strongly connected, you say that it has no cycles. Okay. So all of these properties characterize an arborescence. A graph G has a partial graph. Remember, the partial graph is the one that you get when you, it's not the subgraph, it's the graph that you get when you select arcs or edges, okay? So instead of selecting vertices and whatever connects them, you're selecting specific arcs or edges and etc. So a graph has a partial graph that is an arborescence if it is quasi-strongly connected. So this, if you recall what we did last time, I believe, when we were looking at spanning trees, this is the equivalent of making a spanning tree, but making an arborescence. Okay. So here, what this is saying is, this theorem here says that this graph, which is quasi-strongly connected, there's a way for me to decompose it in such a way that what I have is something resembling something like this. Okay, so I'm going to go pick a root somewhere here, of course, because, well, I have to be able to access all the other vertices. It doesn't really matter which one I pick, provided those guys are somewhere below. Okay? So this would lead to the same sort of mechanism as we saw last time when we were constructing spanning trees. The following result tells us that if we have a simple connected graph and some vertex x1 in there, it is possible to direct all edges. So, sorry, I should stress here, I have xe. So I'm thinking specifically about an undirected graph. Remember, when I have an e there, I mean edge, and therefore there's no direction. So if I have a simple connected graph and some vertex in there, I can direct all edges in the edge set in such a way that the resulting graph, G0, let's say, which is now a directed graph, it has a spanning tree that is an arborescence with that root x1, that the cycles associated with HL circuits, and that the only, what am I called? Yes, exactly. The only elementary circuits of G0 are the cycles that are associated with this spanning tree. So this is again telling us that we can do exactly like we did last time, but in the case of well, we can make a spanning tree, we can make an arborescence, okay, from any graph, connected graph. Okay, this one I am not going to spend a long time on. I just want to bring it to your attention. And I realize that I did not change the definition for these boxes. For propositions, I need to do that, otherwise I disappear behind the propositions. Okay, so when I say counting trees here, I don't mean, what we mean is enumerating, counting how many trees of a certain type are possible. And to do that, and that's sort of an illustration of a whole field, that's the reason why I bring it up. There's a whole industry of the type of thing that I'm going to show you. I'm just going to show you, I think, one or two results. Some of you might become interested in combinatorics. This is like a whole sort of field in combinatorics which studies this type of problem, like how many objects of this type with property X or Y can I find? To do basic counting, you'd have to use this. So the first proposition here, this is just an expansion of some things you have probably seen before. So suppose I have a set that contains n different objects. And then I take integers that sum up to n. Okay, so their sum is n. I take p of these integers, and I'm asking how many ways are there for me to place those n objects that I started with into p boxes that each contain the prescribed number n1 to np of elements or objects. Okay. So that is like one of the base of combinatorics, and there's a formula that's quite well known. So this is I don't even remember what it's called in English, but okay. So it's this n choose n1 to np, let's say, roughly, that is simply defined as the factorial of n divided by the product of the factorials of n1 to np. And then we have what is called the multinomial formula that states the following. So if I have real numbers, this time, here remember I was looking at integers, but I can do that with real numbers. Then A1 to AP, then the sum of A1 to AP to the power n is given by the sum over all possible combinations like this, and I should have added where the n1 to np sum to n. So exactly like here, okay? So all the sums like this of these values times a1 to the n1 all the way to a1 to the np. And I will just make a remark. It is likely that you have seen not the multinomial formula. Those of you doing probability probably have seen it or will see it, but you might have seen the binomial formula, which is just that formula in the case of two boxes. Okay. In French we say urns. I'm not entirely sure that combinatorists in English we put balls into urns. Here we are placing objects into boxes. Same idea. And so yes, as I was saying, so this you know, and I mean, so a plus b squared, the reason why you expand it to 2ab, sorry, plus b squared, you expand it like this, is because of that formula here with just two boxes. And for instance, you probably have seen a plus b cubed. I'm going to write it, but etc. This is one of the classic uses of the binomial formula. Okay. Now, why are those things useful? And you'll see it rapidly becomes complicated. And so I should stress, so this sum that you see here, it is quite complicated, okay? It's a sum over all combination of integers that sum to that value n. It can get quite lengthy. Okay? So let's see an application. If I denote T of n and d1 to dn, the number of distinct trees that have vertices x1 to xn with specified degrees. Okay, so I'm going to say the degree of vertex 1 has to be d1. The degree of vertex n is dn. So I'm imposing n vertices, and I'm also imposing the degrees of the vertices. Well, then we would use that binomial formula. Well, actually here we would use this, okay, to compute this number. And you're going to see a lot of different, if you dig into this, people will say, what's the number of trees that satisfy, etc. And you'll get some formula giving you either an approximation if it's not possible to get it explicitly, or something a bit more explicit if it is possible. And there's a whole industry, as I point out here, of similar results. Okay? Let me point out something that is sort of going to motivate what's coming up later. If we think about trees with vertices x1 to xn, so I'm just thinking about the number of possible trees, okay? So this is not saying, I'm not giving any relation, etc. That number of trees is n to the power n minus 2. So what I really want to stress here is that this becomes big quickly. Okay, so what you have to appreciate is that in this type of problems, it is very quickly overwhelming for a variety of reasons, and that's why we try to find other ways to investigate. Because if I wanted to enumerate every single possible tree, let's say with 100 vertices, then I would be looking at essentially close to a googolplex, okay, which is 10 to the 100, that would be 100 to the 98. These are absolutely colossal numbers, and so you have to realize that, I mean, when you're looking at these permutations of possibilities of what the trees look like, or the trees or graphs, you're looking at a very, very large number. Okay, so I want to take a little break, perhaps erase here, and well, no, actually, let me carry on. We'll see how far I go. I have my time over here, and yes, we're 25 minutes from the full lecture time. I might be able to do everything I want to do now, and if not, we'll carry on to the next lecture. Okay. So, okay, so what I now want to talk a little bit about matrices associated to graphs. And this is an important topic, okay? And I'm just going to review the very base of this. It will come back again later in the course, okay? So there's one or two people here at the UofM who are very, very good at doing this type of thing. Studying the properties of matrices associated with graphs is what is called spectral graph theory. Okay, so it goes both ways, as I will show you. The idea is that you can look at a graph and derive a matrix from it, and from the properties of a graph you obtain properties of a matrix. But we have seen in the first part of this course that it's also easy to obtain some interesting properties from matrices, and so you can take the way back and try to obtain graph properties from the knowledge of the matrices. Okay. So as I said, we are just going to take a brief look into this, but it's an interesting topic. So the first one we've seen already, but I'm repeating the definition here in probably a clearer way than I had done before, because in the previous time we were looking at adjacency matrices potentially for symmetric graphs. Here I'm not imposing this. Okay. So an adjacency matrix is a matrix that you obtain from a graph by just saying that if I have an arc, so you denote I and j the indices of the vertices when you're enumerating them. Okay, so if I have a graph where, so I'm going to to make round vertices to have numbers. Okay, but put numbers in there. Something like this. What I mean here is that I'd have to come up with an order for the vertices. And I would be 1, 2, 3, 4 to indicate whether I'm looking at 1, 3, 7, and 8. Okay, so beware that, you know, like the label for a vertex is not necessarily in increasing order or anything. Typically we try to make them, but it doesn't have to be. Okay. So if I have a graph, the adjacency matrix is simply the matrix that has entry ij equal to 1 if there is an arc in that graph between the first entry and the I and the jth entry, and 0 otherwise. Okay, so we saw that example earlier, well, an example earlier, but let me look at this graph. So in this graph, for instance, I can go from, sorry, I should get some water. I can go from 1 to 2, which is 3 here. I can go here, but I cannot go to the fourth one. From that second vertex, I cannot go here, I cannot go here, I can go here, and that is it. From the third vertex, I can only go to the fourth vertex. And from that vertex, I can go either to the first one or to the second one. So that's the adjacency matrix of this graph. And just to highlight, as I write below, we often write A of G, okay, to really emphasize that it's the adjacency matrix of that graph. And likewise, often you'll see me using the reverse one, which is G of A, because I could give you that matrix and say, well, plot the graph that you get from this matrix, and you would say, okay, I have 4 vertices, and look at, I'm purposefully changing the index on the matrices. I have 4 vertices. From the first one, I can go to the second and the third. From the second, I can go to the third. From the third, I can go to the fourth. And from the fourth, I can go to the first and the second. Okay, so that, in a sense, would be G of A. Okay. Of course, if my graph is undirected, then I don't need to know the direction of the arrows. And that's what we saw last time when I was talking about adjacency matrices before. That gets a little messy. The matrix associated to a graph that has no direction is, of course, symmetric, because there would be an edge here. So I can go from 1 to 2, but also from 2 to 1. And if I have non-zero diagonal entries, it means the graph is not simple, because that would mean that, for example, I can go from 1 to 1, which in practice, here, would add a 1. Okay. So that's the adjacency matrix. Now, you can have an adjacency matrix as well when you're looking at the multigraph case. So in a multigraph case, you would indicate how many arrows there are in each direction. So if perhaps I'm an idiot, I should have kept this. Let me just change. Let me keep the matrix with just vertices 1, 2, 3, and 4. And so you probably hear me breathing heavily after I do that, because you have to push rather intensely on the bloody thing to make it disappear, but that's another problem. Okay, so let's suppose this is a multigraph. How would I make a multigraph out of this? Well, I could say, for instance, that there are 3 arrows here and 2 arrows here. Well, how would I change the matrix to change this? Well, here I would have a 3. So that was from 1 I can go here and not here. From 2 to 3 I have 2 arrows. Okay, so all I do is count the arrows. That's it. From 3 I have just an arrow to 4, and from 4 I have the 2 arrows that I had already indicated. Okay, so in a multi-graph case, the numbers indicate how many arrows there are between each pair of vertices. The same way as with the simple graph, if the graph is undirected, then that matrix is going to be symmetric. And this is exactly what I had here. I have non-zero diagonal entries if the graph is not simple. Another thing that you will see from time to time, and we might use it later because that's quite useful in some applications, would be weighted adjacency matrices. So sometimes you'd get numbers in your adjacency matrix, but those numbers would not come from the fact that you're counting the number of arrows, but that for some reason you decided to put a weight on the edges or the arcs. Okay, and that's so one type of graph where this happens a lot. For instance, for those of you who are in stats, or other domains, but in stats in particular, if you see a Markov chain, discrete time Markov chain, the edges, actually the arcs in a Markov chain, represent the probability that you will switch from one state to another. So you could have, let me produce a simple example of this. Here is a sort of very naive and completely artificial example of a Markov chain I had made up in class, in a modeling class years ago. So the idea was to say, well, in Winnipeg, for instance, during the winter, there will be very cold or very, very cold days. And then there will be very cold days and cold days and warm days. And a Markov chain is a stochastic process that switches between those states with a certain probability. And so, for instance, you would say the state on one day is the state, and then I'm switching to other states the next day for some reason. And typically I assign completely silly values to this, which would be something like, well, if it's very, very cold, the probability that it's still very, very cold the next day, let's say, is 20%. And otherwise, it will be very cold in 80% of the cases. If it's very cold, the probability that it remains very cold is 50%. And then with some probability 0.1, I would switch back into a state where it's very, very cold. And then the remainder is, where am I? 0.4 would be, well, it's cold. If it's cold, then typically it will remain cold most of the time, let's say. And if you're a bit lucky, or let's say almost all the time, if you're a bit lucky, it becomes warm. But otherwise, you're unlucky and it becomes very, very cold. Never goes back through cold. And vice versa. And here, if it's warm, well, you're almost assured that it's not going to remain warm. It's going to be either, let's say, very cold, cold, very cold, or very, very cold. Yes. So this matrix is, by the way, if I look at the matrix here, let me show you, so I can write the states. Let me list them as VVC, VC, C, and W. So in my adjacency matrix, what I would have is my weighted adjacency matrix. I would have 0.2 here. I would have 0.8 here. Nothing, nothing. Then from here, I'd have 0.5. Wait, first I'm looking at moving back to very, very cold. Then I have 0.5 there. Then I have 0.4 here. From here I have 0.8. I can move here with 0.1 probability. I cannot move here. I can stay here with 0.8 and therefore. And finally, if I'm here, what did I write? I need to do them in this order. I have 0.3 here. I have 0.4 here. And 0.3 here. And the reason I decided in the end to write down this matrix is, if you check, this is a stochastic matrix. Okay? You can see that each row sums to 1, because when I'm in a state, I need to be in a state, another one or the same the next day. I don't have a choice. I have to go somewhere. And therefore, the sum of the probabilities of movement to somewhere else is 1. And this is a weighted adjacency matrix. And for those of you who are interested in Markov chains, this is an interesting connection. Okay, you can see I'm talking about graphs, but I'm also talking about matrices and probability at the same time, and these mix all the three. So that's one reason, but it's not the only one, why you would assign a weight to an edge. And in that case, you have a matrix like this. Not necessarily stochastic. Okay, I've taken an example where it's stochastic, but that doesn't make it necessary. We then speak in general about the spectrum of a graph. Okay. And we'll come back to that. Okay. But for now, let's just look at the definition. The definition will be that we call spectrum of a graph. This is simply the spectrum, so the set of eigenvalues, of the associated adjacency matrix. Okay? So when you can see the connection. So the spectrum of a graph is the spectrum of the adjacency matrix. And that will have important properties in terms of characterizing properties, like some characteristics of the graph. And I need to erase again. Another type of matrix associated to a graph is what is called the incidence matrix. So in this case, the definition is going to be a bit different depending on whether we are in the directed or undirected case. The idea is the same. Okay, so what we do is, suppose you have a graph of order n, so with n vertices, and p edges. That's the undirected case. Okay. We call incidence matrix the matrix that has n rows and p columns, where we put the vertices in the rows and the edges as the columns, and we put a 1 in a position if there is an edge that's incident to that vertex. So let me show you a simple example. So suppose this is vertex 1, edge 1. It's not very, oops, sorry, edge, not arc. So edge 1, this is edge 2, and this is vertex 3. And then let me say that there is a 4 here, and that is 4. This is not very clever. Probably let me change this just a tad. Let me make this A, B, C, D. So that it's a bit clearer. Okay, the vertices are the letters and the edges are the numbers. Then the matrix would be a matrix that has A, B, C, D as the rows, and one, or let me add one just for sure. 1, 2, 3, 4, 5 as columns, and in which there would be a 1 if the edge is incident to the vertex. So A is incident to 1, so there's a 1 here. A is incident to nothing else, so, whoops, got number 3 there. B is incident to 1, 2, and 4. And that's it. C is incident to 2 and 5. And D is incident to 4 and 5. So the incidence matrix would be the matrix. Of course, you can remove the I don't know if those are not better. Okay, you can remove your help on the side. So that's the incidence matrix for this graph. In a case of a directed graph, we add one additional piece of information, which is the direction in which the arc is incident. Okay, so you have a 1 if the arc enters, and a -1, sorry, if the arc leaves. So suppose I were to add a direction on these guys, like this, then that matrix now in the directed case would be, okay, from A, this arc is leaving A, and there's nothing else. In B, this arc is coming with a +1. This arc is coming with a +1, arc 2. Arc 4 is leaving. C, from C, I am leaving along arc 2, and I am entering along arc 1. And lastly, from D, I am entering from 4 and leaving from 5, along 5. Okay. And that gives me the incidence matrix. And judging by the time, I think I have to stop here. So I will continue this in the next lecture.